In 1876, the United States was celebrating something enormous. 100 years of independence. 100 years of survival, expansion, and transformation. To mark the moment, the country organized a Centennial International Exhibition in Philadelphia, the largest technological exhibition the world had ever seen. People traveled from every corner of America and from dozens of other nations just to witness it. And when they walked through the gates, they entered a world that felt like stepping into the future. At the center of the exhibition stood a building called Machinery Hall. It stretched across 13 acres under one enormous roof. Inside, hundreds of machines ran simultaneously. Looms snapped threads into cloth. Printing presses hammered ink onto paper. Lathes carved steel with sparks flying across the floor. The air smelled like oil, coal smoke, and hot metal. The floor trembled constantly from the rhythm of machinery. For many visitors, this was the first time in their lives they had ever seen industrial machines working together at this scale. But what almost nobody realized was that every single machine in that massive building was being powered by one engine. Hidden in plain sight, standing at the center of Machinery Hall, was the largest steam engine most people had ever seen. It was built by a Rhode Island engineer named George Henry Corliss, and it was unlike anything that had come before it. Two towering cylinders drove a giant crankshaft mounted high above the floor. And attached to that shaft was the heart of the entire system, a flywheel so massive it looked like something that belonged to a shipyard rather than a building. The wheel was 30 feet across. It weighed 56 tons. And when the engine started, that enormous ring of cast iron began to turn, slowly at first, then faster and faster. Soon the outer rim of the wheel was traveling nearly 45 miles per hour. Visitors gathered around it in fascination. Children pointed upward at the spinning iron giant. Engineers studied its design. Politicians proudly described it as proof that America had become an industrial power. President Ulysses S. Grant himself helped start the machine on opening day, while the Emperor of Brazil stood beside him watching the moment unfold. To the public, it looked like a triumph, a masterpiece of engineering, a symbol of the future. But there was something about that wheel the crowd didn't understand. That spinning iron circle was storing an unimaginable amount of energy, more energy than most people in that building could even comprehend. And if the metal holding it together failed, even for a fraction of a second, that wheel wouldn't just stop. It would explode. Fragments of iron weighing hundreds of pounds would launch outward at highway speed. Through machines, through walls, through the crowd standing only a few dozen feet away. And in 1876, there were no safety barriers, no protective enclosures, no warning signs. For 6 straight months, nearly 10 million people walked through Machinery Hall, standing within range of that spinning flywheel. They admired it. They photographed it. They talked about how powerful and beautiful it was. But almost none of them stopped to ask the most important question. What would happen if it broke? And that question, the one nobody in that building asked, is where this story truly begins. But before we go deeper into the machine itself, quick pause for a second. If you enjoy stories about the forgotten machines that built the modern world, consider subscribing to the channel. Every week we explore another piece of industrial history. The machines, the engineering, and sometimes the disasters that shaped our world. Now, let's step deeper into the factories of the 19th century. Because to understand why this machine existed, we first have to understand how factories were powered before electricity even existed. To understand why the giant engine in Machinery Hall was so important, you first have to understand how factories worked in the 1800s. Because the world of industry back then looked nothing like the factories we know today. There were no electric motors attached to individual machines, no switches on the wall, no control panels, no emergency stop buttons. Instead, an entire factory depended on one single source of power. At one end of the building sat a massive steam engine. It burned coal or wood to heat water inside a boiler. As the water turned into steam, pressure built inside the metal chamber. That pressure drove pistons back and forth, and those pistons turned a rotating shaft. That spinning shaft was the heartbeat of the entire factory. From it, long steel rods ran across the ceiling of the building. These rods were called line shafts, and they stretched from one end of the factory floor to the other like the spine of a mechanical creature. Attached to those shafts were dozens, sometimes hundreds, of leather belts. Each belt dropped down from the ceiling and wrapped around a pulley connected to a machine below. A loom, a drill press, a saw, a lathe. When the shaft turned, every belt began to move. And when the belts moved, every machine in the building came alive. Imagine walking into a factory like that. Overhead, steel shafts rotated continuously, their surfaces polished by years of motion. Leather belts snapped and fluttered as they carried power down to machines. The air was filled with the smell of oil and dust. The floor vibrated beneath your feet. And everywhere you looked, something was moving. The belts themselves were incredibly fast. Some moved at speeds close to a galloping horse. Workers who maintained those belts had to climb through narrow spaces where spinning machinery passed just inches from their heads. One mistake was enough. If a loose sleeve caught the belt, if a hand slipped too close to the pulley, if a worker stumbled into the moving shaft, the machine didn't stop. It couldn't. The entire building depended on that motion. But even those spinning belts were not the most dangerous part of the system. The real danger was hidden inside the engine room, because at the center of the steam engine, mounted directly on the main shaft, sat the machine's most critical component, the flywheel. Steam engines do not produce smooth power. The pistons inside them fire in bursts. Each stroke delivers a sudden push of force followed by a moment of weakness before the next stroke begins. Without a flywheel, that uneven power would shake machines violently and tear belts apart. So engineers added a massive rotating wheel to the shaft. The flywheel absorbed the burst of energy from each piston stroke and released that energy gradually between them. The result was a smooth, steady motion that kept the factory running evenly. But there was a trade-off. The bigger the flywheel, the more energy it could store. And by the 1870s, engineers were building flywheels that weighed 20, 30, even 50 tons. They looked calm while they spun. Silent, smooth, predictable. But inside that motion was something terrifying. The rim of a giant flywheel could store the same amount of mechanical energy as an industrial boiler under pressure. Not heat, not fire, but pure rotating force. And if that iron wheel ever failed, all of that energy would be released in a single violent instant. Which brings us back to the machine George Corliss built for the Centennial Exhibition. Because the engine and machinery hall wasn't just another factory engine. It was the largest engine anyone had ever attempted to build. Long before the Centennial Exhibition opened its doors in 1876, there was a man whose name had already become legendary in American industry. His name was George Henry Corliss. Corliss was not a politician. He wasn't a wealthy industrial baron either. He was something far more important to the 19th century machine world, an engineer who understood how to make power behave. Born in 1817 in New York, and later working in Providence, Rhode Island, Corliss spent most of his life surrounded by metal, gears, pistons, and steam. At a time when steam engines were already driving factories across America, he realized something crucial. Most engines of that era were incredibly wasteful. They burned massive amounts of coal just to keep running. Their motion was uneven, their efficiency poor, and their reliability questionable. Factory owners constantly dealt with engines that stalled, broke, or wasted fuel. Corliss believed he could fix that. In the 1840s, he developed an innovation that would change steam engines forever, the Corliss valve gear. It may sound like a small technical improvement, but the effect was enormous. The valve system controlled how steam entered and exited the engine cylinders. Instead of allowing steam to flow continuously, Corliss designed a system that admitted steam precisely when it was needed and cut it off at exactly the right moment. The result was revolutionary. Corliss engines used far less fuel, ran smoother, and produced more reliable power than almost any engine built before them. Factory owners quickly noticed. Within a few decades, Corliss engines were powering textile mills in New England, steel plants in Pennsylvania, and factories across the rapidly industrializing United States. By the 1870s, Corliss had become one of the most respected engineers in America. So when the organizers of the Centennial International Exhibition began planning Machinery Hall, the enormous building that would showcase the industrial future of the country, they faced a serious challenge. They needed a single engine powerful enough to drive every machine in the hall, not just a few machines. All of them. Printing presses, lathes, looms, metal cutters, pumps, hundreds of pieces of equipment spread across 13 acres of floor space. No engine of that scale had ever been attempted. The exhibition committee approached Corliss with the idea: build the largest steam engine in the world, an engine that could run continuously for 6 months in front of millions of visitors. And Corliss agreed. But he made one unusual decision. Instead of building the engine for payment, Corliss funded much of the project himself. His only condition was that once the exhibition ended, the machine would belong to him. Why? Because he understood something the committee did not. If the engine succeeded, it would become the most powerful advertisement his company could ever have. For 2 years, Corliss and his engineers worked in Providence designing and assembling the enormous machine. Piece by piece, the giant engine began to take shape. Massive steam cylinders, a towering crankshaft, and at the center of everything, a flywheel so large that no foundry on Earth could cast it in one piece. Instead, it would have to be assembled from multiple sections of iron, each bolted together to form a ring 30 feet across. When the final design was complete, the entire engine weighed more than 700 tons. It was the largest steam engine ever built. And in 1876, it would stand in the center of Machinery Hall as the beating heart of America's industrial future. But there was still one problem. A wheel that size had never been tested before, and nobody truly knew what forces it would unleash once it started spinning. At the heart of the Corliss Centennial engine was a machine component that looked deceptively simple. A wheel, but not just any wheel. This one was 30 feet in diameter, taller than a 3-story building, and weighed 56 tons. When visitors entered Machinery Hall, many of them noticed it immediately. The giant iron circle dominated the center of the engine, like the orbit of a mechanical planet. To the crowd, it looked almost graceful, smooth, balanced, quiet. But in reality, that spinning ring of cast iron was storing a terrifying amount of energy. The flywheel existed for a very specific reason. Steam engines produce power in bursts. Each piston stroke pushes with force, then briefly relaxes before the next stroke begins. If that uneven motion traveled directly into the factory's machinery, every loom, lathe, and press would jerk violently. The flywheel solved that problem. It acted like a mechanical battery. Every time the piston fired, the wheel absorbed some of the energy and stored it in its rotation. Then, between piston strokes, it released that energy back into the system, keeping the motion smooth and steady. But storing energy requires mass, and lots of it. The heavier the wheel, the more energy it could hold. That's why Corliss built a flywheel so enormous that no single founder in America could cast it in one piece. Instead, the wheel had to be built like a giant mechanical puzzle. Curved iron segments were cast separately and then bolted together around the rim. Massive steel bolts held each section in place, forming a continuous circle of metal. Every one of those joints carried enormous stress once the engine started running. Because when the flywheel reached full speed, something remarkable happened. The outer edge of the wheel began moving at almost 45 miles per hour. Think about that for a moment. Not a car, not a train, a ring of iron weighing more than a locomotive spinning inside a building, with its rim traveling at highway speed. And unlike steel, the material used in most modern machines, cast iron behaves very differently under stress. Steel bends before it fails. It stretches. It warps. It gives warning. Cast iron does not. It holds its shape perfectly, right up until the moment it breaks. And when cast iron fails, it doesn't crack slowly. It shatters. Engineers studying flywheel accidents later discovered something disturbing about these failures. When a flywheel breaks, the pieces do not simply drop to the floor. Each fragment continues moving in the direction it was already traveling. Imagine a 300-pound chunk of iron flying through the air at highway speed. Now imagine dozens of those fragments launching outward at the same time, through machines, through walls, through anything standing nearby. Investigations of industrial accidents in the late 19th century found flywheel fragments embedded in brick walls, buried deep in factory yards, and scattered hundreds of feet away from the original engine room. The energy stored inside those spinning rims was enormous. And in 1876, inside Machinery Hall, that same kind of flywheel was turning only 30 feet away from thousands of visitors. No steel guard surrounded it. No protective barrier separated the crowd from the machine. Just open space. The wheel spun calmly, almost peacefully, as if it had nothing dangerous hidden inside it. But the truth was very different. That flywheel wasn't just a machine part. It was a 56-ton reservoir of stored violence. And every person in Machinery Hall was standing well within its reach. Long before safety barriers, warning labels, or emergency shut-off systems existed, factories depended on one group of men more than any other: the engine room operators. These were the workers responsible for keeping the steam engines running. The men who stood closest to the giant flywheels that powered entire factories. And in the industrial world of the 19th century, their job was considered both the most respected and the most dangerous position in the building, because every machine on the factory floor depended on them. Inside the engine room, the environment felt completely different from the rest of the factory. The moment you stepped through the door, the air changed. The smell of hot oil, coal smoke, and heated iron filled your lungs. The temperature was often far higher than the rest of the building, because massive boilers burned constantly nearby. The walls vibrated with the rhythm of machinery. And above all of it, dominating the room like the center of gravity itself, the giant flywheel turned endlessly. Slow, smooth, almost hypnotic. For new workers, the wheel looked strangely calm. After a few days in the engine room, the steady hum of the machine became background noise. But experienced engineers never forgot what it truly was: a massive store of mechanical energy. They knew that if the wheel failed, no one in the room would have time to react. That knowledge shaped the way they worked. During a typical shift, operators constantly inspected the engine. They watched the pressure gauges that measured steam inside the boiler. Too little pressure, and the factory machines would slow down. Too much pressure, and the boiler itself could explode. They listened to the rhythm of the pistons. An experienced engineer could hear problems before they became visible. A subtle change in sound might mean a valve was sticking. A vibration in the floor could mean the shaft bearings were wearing down. Every bolt, every connection, every moving surface had to be watched carefully, because the engine never stopped. Factories in the 19th century usually ran 12 hours a day, 6 days a week. Some mills operated even longer during periods of high demand. Shutting the engine down meant stopping production across the entire building. And stopping production meant losing money. So the engine ran continuously. The men responsible for it had to remain alert the entire time. Imagine standing in that room for 12 hours. The floor constantly trembling beneath your boots. Leather belts snapping overhead. Steam hissing from valves. And beside you, a 30-foot iron wheel spinning faster than a galloping horse. That was the daily reality for the engine crews who ran machines like the Corliss engine. Despite the risk, these men were some of the highest paid workers in the factory. Not because the job was comfortable, but because very few people were willing to do it. The operators understood the machines better than anyone else. They knew how to adjust steam valves, tighten bolts, lubricate bearings, and keep the engine balanced under enormous stress. They also knew the stories. Industrial workers shared news the same way sailors shared stories of storms. From mill to mill, from city to city, tales spread about engines that failed. A flywheel that shattered in Pennsylvania. An iron fragment that punched through a brick wall in Massachusetts. Workers killed instantly when a machine suddenly exploded beside them. Those stories traveled through workshops and engine rooms across the country. And yet, every morning the operators returned to their posts. They checked the pressure gauges. They listened to the pistons. They watched the wheel, because the factory depended on them. And because the truth of the industrial age was simple. If the machine stopped, the pay stopped. And for most workers in the 19th century, that was a risk they simply couldn't afford to take. For most people visiting factories in the late 1800s, giant machines like flywheels looked impressive, even beautiful. They turned with a calm steady motion. Their polished iron surfaces reflected the dim factory lights. The engines hummed with a rhythm that sounded almost peaceful. But engineers and mechanics who worked around these machines knew something the public rarely understood. A large flywheel was not just a machine part. It was a loaded weapon made of iron. Because when a flywheel failed, it did not simply stop. It exploded. To understand why, you have to think about what happens when something extremely heavy spins very fast. As the wheel rotates, every pound of iron in the rim wants to fly outward. Engineers call this centrifugal force. The faster the wheel spins, the harder the metal pulls against itself. That tension is enormous. In giant industrial flywheels, thousands of tons of force are constantly trying to tear the rim apart. As long as the iron holds together, everything works perfectly. The wheel spins smoothly. The engine runs quietly. The factory continues producing goods hour after hour. But if even a tiny flaw exists inside the metal, a crack, an air bubble from the casting process, or a weak bolt at one of the joints, the result can be catastrophic. Because cast iron behaves very differently from steel. Steel bends when pushed too far. It stretches and deforms before finally breaking. Cast iron does not. Cast iron holds its shape perfectly until the exact moment the stress exceeds its limit. Then it shatters instantly. When that happens inside a spinning flywheel, the stored energy inside the wheel releases all at once. And the results are terrifying. Investigations into flywheel accidents during the 19th century found fragments of iron weighing several hundred pounds scattered across factory yards. Some pieces punched straight through brick walls. Others buried themselves deep in the ground outside engine rooms. In one documented case in Pennsylvania, engineers discovered a section of a shattered flywheel embedded more than 100 feet away from the machine. Think about that. A piece of iron heavier than a motorcycle thrown across an entire football field, inside a factory building filled with workers. And the most frightening part was how suddenly it happened. Workers who survived these accidents often reported the same thing. There was no warning, no grinding sound, no shaking, no slow cracking noise. The engine simply ran normally until it didn't. In 1891, a massive flywheel shattered inside the Amoscake Manufacturing Company textile mill in Manchester, New Hampshire. The wheel weighed nearly the same as the one used in the Centennial Exhibition, 56 tons. When it failed, the iron rim exploded into fragments that ripped through the engine house. 3 workers were killed instantly. Iron pieces punched through the brick walls of the building and landed across the mill yard. Other fragments damaged nearby structures hundreds of feet away. Investigators later determined that the flywheel had been operating normally before the failure. The metal simply reached its breaking point. Events like this forced engineers to confront a disturbing reality. The most dangerous machines in industrial history were often the ones that looked the calmest. A giant flywheel spinning quietly in the corner of a factory might be storing more destructive energy than an entire steam boiler. And that brings us back to the coreless Centennial engine. Because in 1876, inside Machinery Hall in Philadelphia, a flywheel just as large and made of the same cast iron was spinning only a few dozen feet away from thousands of visitors every day for 6 straight months. And none of them had any idea how close they were standing to a potential industrial disaster. By the summer of 1876, the Centennial Exhibition in Philadelphia had become something much larger than a celebration. It had turned into a statement about what the United States had become after 100 years of existence. Only a decade earlier, the country had survived a brutal civil war that killed more than 600,000 people. Entire cities had been destroyed. The national economy was shaken. For many nations watching from across the Atlantic, the question was simple. Would the United States recover or collapse? The Centennial Exhibition was America's answer, and at the center of that answer stood a machine, the coreless Centennial engine. Inside Machinery Hall, thousands of machines from across the industrial world were running simultaneously. Printing presses from Europe, American metalworking tools, textile machines, pumps, and mechanical devices filled the enormous building. Every single one of them depended on a single source of power, the coreless engine. Visitors entering the hall experienced something almost overwhelming. The sound alone was unforgettable. Instead of the quiet hum of a modern factory, Machinery Hall produced a layered mechanical roar. Hundreds of machines moving at once, belts slapping overhead, metal striking metal, steam hissing from valves, and beneath all of it, a deep rhythmic vibration pulsing through the floor. The entire building felt alive. At the center of that mechanical storm stood the giant engine. Two towering steam cylinders drove the massive crankshaft. The crankshaft turned the enormous flywheel. From there, power traveled through long shafts that stretched across the entire building. Leather belts carried that motion down to every individual machine. It was like watching a mechanical nervous system. One heart, hundreds of moving limbs, all working together. On May 10th, 1876, opening day of the exhibition, two important figures stepped forward to start the machine. President Ulysses S. Grant, the leader who had guided the Union to victory in the Civil War, stood beside Dom Pedro II, the Emperor of Brazil, in front of a crowd of more than 100,000 spectators. They pulled the starting levers. Steam rushed into the cylinders. The pistons began to move. Slowly, the giant flywheel started to turn. At first, the motion was almost hesitant. Then the engine found its rhythm. The wheel spun faster and faster until the enormous iron rim blurred into motion. And suddenly, across Machinery Hall, the entire building came alive. Belts snapped into motion. Lathes began cutting metal. Printing presses started hammering ink onto paper. Within minutes, newspapers printed inside the building were already being handed to visitors walking through the aisles. It was an unforgettable moment. Witnesses described the experience as if a mechanical wind had filled the hall. The building vibrated with energy. Machines clattered and roared in perfect synchronization. Dom Pedro, too, reportedly stood up from his chair in astonishment. He had toured factories across Europe and South America, but he had never seen anything like this. For the next 6 months, the engine ran continuously, day after day, powering 13 acres of machinery. Nearly 10 million visitors walked through Machinery Hall during the exhibition. They watched the flywheel spin. They admired the engineering. They celebrated the machine as proof that the United States had entered a new era of industrial power. To them, the engine represented the future, a future where machines would produce goods faster than human hands ever could. A future where industry would reshape cities, economies, and entire nations. But what none of those visitors fully realized was that the age of giant central engines like the Corliss machine was already approaching its end, because a new kind of power was quietly beginning to spread. Electricity. And once electricity entered the factory floor, the industrial world would never look the same again. For 6 months in 1876, the Corliss Centennial engine stood at the center of Machinery Hall like the beating heart of industrial civilization. Day after day, it turned. The giant flywheel rotated with calm precision. Leather belts carried its power across the hall. Hundreds of machines worked in perfect mechanical rhythm. Nearly 10 million visitors walked through the building during the exhibition. Farmers from the Midwest, engineers from Europe, businessmen from New York, entire families traveling just to see what the future of industry looked like. And at the center of that future stood the enormous steam engine. To the people who witnessed it, the machine felt permanent. Something so large, so powerful, and so impressive seemed impossible to replace. But history rarely works that way. Because while the Corliss engine was running inside Machinery Hall, a new kind of power was already beginning to reshape industry. Electricity. Unlike steam engines, electric motors did not require giant boilers, spinning shafts, and enormous flywheels. Instead of powering an entire building from a single machine, electricity allowed factories to attach small motors directly to individual machines. That one change transformed everything. Factories no longer needed long overhead shafts stretching across the ceiling. Leather belts disappeared. Dangerous spinning flywheels became unnecessary. And, perhaps most importantly, if one machine failed, the rest of the factory could continue working. The old system, the one the Corliss engine represented, slowly began to fade. But the engine itself did not disappear immediately. When the Centennial Exhibition closed in November of 1876, the massive machine was carefully dismantled and shipped west to Chicago. There, It was installed inside the Pullman Palace Car Company, a factory famous for building luxurious railroad sleeping cars. Inside the Pullman works, the giant engine returned to what it had been designed for in the first place: industrial work. For years it powered machines that produced railroad cars traveling across the expanding American rail network. But something interesting happened. The most famous machine in America quietly became just another factory engine. Workers inside the Pullman plant likely walked past the giant flywheel every day without realizing that it had once been the centerpiece of the greatest exhibition in the country's history. The machine kept turning, year after year, until eventually even giants become outdated. By the early 20th century, electric motors had taken over most industrial power systems. Factories no longer needed massive steam engines driving entire buildings. They needed smaller, more flexible machines. The coreless engine was dismantled, and like thousands of industrial machines before it, the iron was melted down and reused. No ceremony marked its end. No monument preserved it. The machine that had once powered the future of American industry simply vanished. Today, Machinery Hall itself no longer exists. The building burned down shortly after the exhibition closed. The enormous stone foundations that once supported the 700-ton engine were eventually covered by grass in Fairmount Park. Most visitors walking to the park today have no idea what once stood there, yet the story of the coreless engine still matters, because it represents something larger than one machine. It represents the moment when human industry began operating on a scale the world had never seen before, a time when engineers pushed technology to its limits, when factories grew into mechanical cities, and when men stood beside machines powerful enough to reshape entire economies. For 6 months in 1876, a 56-ton flywheel spun at the center of Machinery Hall while 10 million people watched. They saw progress. They saw the future. But they never saw the invisible forces stored inside that spinning iron wheel. And maybe that's the most interesting part of the entire story. Because sometimes the machines that build the modern world are also the ones we forget the fastest.